So I think we should probably start. So it's a great pleasure to welcome Chan today, Dr. Chan from King's College London. He's the director of robot perception lab. So Chan and I, as I said, so Chan and I have known each other for a few years now. I've always really admired his work on tactile perception. So I'm just going to give like a brief introduction of Shan, and then so Shan he graduated from King's College London for his PhD in tactile manipulation, and then he then moved to he also actually at that time visited MIT to work with Edward, who if you know, Edward is the inventor of GeoSight. So he has been really working at the forefront of tactile sensing, and then he did his postdoc at Leeds and also Harvard University. So then he moved on. He moved on to Liverpool to take as a director of that time Smart Lab, if I remember, Smart Lab in Liverpool, and then he's now moving back to where he got his PhD, which is King's College London, as a reader in robotics and AI. Shan has got many awards, for instance, one of the very prestigious one is the UK Russ Early Career Award. That is really prestigious. It means that he is one of the best in the UK doing robotics as an early career researcher. And he's got lots of fundings. He got, if I remember correctly, 1.5 million funding as PI. And he's got his NIA. He also has very strong connection with the Univer, where he's doing a lot of works on tactile sensing as well. So you know that I know him really well. I don't even need any transcript to say anything about him. So without further ado, I would just take the floor here with Shan, so he can start with his talk.
Thank you, Jihong. Thank you for your invitation. It's my great pleasure to be here to share our research. I think it's my second time to be in York. Last time was many years ago, and it's a very nice city and a very nice campus compared to King's. You have a lake. Yeah, we can't have a lake. Our research has been focusing on robot visual-tactile intelligence. So today we'll have a focus on data generation for visual-tactile sensing. So we can start with something in ourselves. So the human visual-tactile intelligence, what it is and how it can inspire the robot development. So in our daily life, we are frequently using vision and tactile sensing in dexterous tasks. Yeah. So these are two examples. One example is how you can sort these clothes when to laundry. So you can see you are using your eyes and also your fingers to do this task. So your eyes can guide the motion of the fingers, and then the tactile sensing in the fingertips can tell you the texture, stiffness of the fabrics, and then you can sort out these clothes in different baskets. Another example is how when you do this manipulation task using a needle, and also you have the cloth and you have the needle, and it's quite dexterous as you have to coordinate vision and tactile sensing in localizing the needle and also the place you want to go through the clothes. So that's why it's very important to coordinate both vision and tactile sensing in such tasks. So these are based on our own experiences. Also, there are some other examples like very related to our research. For example, when you do this task, you can feel the properties of your hair. So this with tactile sensing. And also sometimes it can be done with vision. So for robotics, we have vision and also tactile sensing as well. Vision is quite common now. We have seen a lot of cameras. So we have RGB cameras and also the depth cameras. And from there, you can get a lot of applications, operator cognition, manipulation, and vision-based tactile sensors, and like what we do in our research. And also you have the human-machine interaction. For tactile sensing, you have information like force, sleep, these contact interactions with these objects. And there are different types of sensors, like force, torque sensors, or capacitive sensors. And also you can sense temperature, humidity from these tactile sensors. And you can also do object recognition in a different way compared to vision. You can get hardness, texture, frequency coefficients, and also geometry of the object. And also you can do physical human-robot interaction. So this the perception part, and then from there you can integrate data from vision and tactile sensing. You can get a better perception of these objects, and then you can do these manipulation tasks. So you can have like the closest sorting task we have seen in the previous slides. So this is a very brief overview of what we can do with vision and the tactile sensing. So from there, we have a few strands of research in our lab. The very first strand is vision-based tactile sensors, so the hardware. So as we know, we have different sensors for vision. We have the RGB cameras or depth sensors. They are quite well established. You can buy these sensors from the market, but we don't have many available for tactile sensors. Yeah. So we have got many inspirations from the common modalities of vision and tactile sensing. So for RGB cameras or depth sensors, they are in the format of pixels. Yeah. So this is a picture. Probably you can see it's a picture of Lincoln. And this picture is formed in a run of pixels. So with these density values for each pixel, and then you can get these features: its eyes, nose, mouth, and also the profile of the face. So that's how we do feature extraction from a video image. So this can give you a lot of visual information. So from there, we have also seen the application of visual sensing in tactile sensing. So that's how we have vision-based tactile sensing. One good example is the gel size sensor. So we have a camera at the base, so here, and we have a few LEDs of different colors to illuminate the sensor space. And then we have a layer of elastomer on the top. So the camera can capture the deformation of the elastomer. And we have a reflective layer on the top of the elastomer so that we can reflect the LED lights back to the camera. So that's how we get the tactile images. So this is one example. We have the gel size sensor on the left, and we have the view from the camera inside the sensor on the right. So from there, you can see you can get very detailed textures from the tactile images, like the fingerprints of fingertips. And also we can have different modes of the gel size sensor. You can have a plain elastomer without any markers. You can get a very detailed texture, but also you can get these select markers. So these are these markers printed on the inner surface of the elastomer, so that you can track the motion of these markers when they move. So this can give you some information like force or the sleep between the object and sensor. From vision-based tactile sensing, it can offer you a lot of advantages, such as high resolution. It's camera-based, so that's why you can get a tactile image instead of these taxels, or irons. So for traditional tactile sensors, usually we can get taxels of around like 100 maximum, I would say. But for vision-based tactile sensing, you have the resolution as the camera. So that's very high resolution for tactile sensing. And then you can get very rich information like texture, force, sleep, very rich physical interactions between the object and the sensor. And also it's natural for visual tactile integration. Essentially, it's a visual modality. Yeah, so you're using the visual modality for tactile sensing. So that's why you can use techniques like convolutional neural networks to process the tactile images. So these are the advantages offered by vision-based tactile sensing. So from there, we have seen there are few gaps in vision-based tactile sensing. From gel side, you can see it's a flat surface. You can only sense the contact on the flat area. Yeah, and you can't sense the size or the tip of the robotic finger. So that's why we came up this new design we call GelTip. It's the first omnidirectional high-resolution finger tactile sensor. So the sensing principle is similar to the gel size. We have a camera as the base, and we have LEDs of different colors, so we can illuminate the sensor space. And also we have a layer of elastomer covered on the sensor surface. And we have one layer of reflective material so that the light can be reflected back to the camera. And then you can get the tactile image. But the main novelty lies in the morphology of the sensor itself. It's like a finger. The camera can detect the contact around the finger, not only in one small area in the grasp, inside the grasp, like the gel side. And this is a figure of the GelTip sensor we have developed. And this is one example output from the sensor. As you can see here, if we use the GelTip sensor to grasp one strawberry, we can get very detailed texture of the strawberry. Yeah, so including the seeds in the strawberry. And then in this video, as we can see, when we apply this tactile sensor to pad a 3D printed object, so we can detect the contact around the finger. So that's how we call it omnidirectional tactile sensing. And this can be very helpful for different applications. For example, when you have the grasping and manipulation in cluttered environments, the contacts can come from different directions. So this can be useful for these applications. And from there, we have got different prototypes in the hardware. One is TouchRoller, and this can be useful for the large area assessment. So from the previous slides, as you can see for the gel side or the GelTip, so the sensing area is quite limited. And when you get the perception task, you have to tap one by one. But if you have a rolling mechanism, you can roll over the large area. So for example, here we have a piece of fabric, and we can just roll over this TouchRoller. It has a roller shape, and we can just roll over this tactile sensor over this fabric. And we can integrate all the tactile images together so you can get a global view of the fabric texture. So that's how we call it the TouchRoller. And another work we have got is a tactile sensor with a rotating camera. So instead of rotating the sensor itself, we are rotating the camera inside the sensor. So as you can see here, we can rotate the camera inside the sensor from one angle to another and to another. Then you can stitch them together as well. And with one contact, you can get quite a few tactile images, and then you can get a large area of contact. So we call it GelFinger. It has a finger shape, but it can rotate the camera so that we can get the perception of a larger area. And recently we have got one step further, and we have the RoTipBot. We add one additional this motor to the base of the sensor so that we can rotate the sensor itself. So that's how we call it the RoTip. It can rotate. So this is with one particular application in mind, handling flexible and thin objects, so like paper or the thin film in manufacturing. So they are quite common in our daily life and also in factories. With the previous sensors like gel sites, GelTip, also like the GelFinger sensors, they can't handle these objects, and they are quite thin and they are flexible. So here with the rotational mechanism, we can rotate each layer of this object, and we can fit these objects into the center of the gripper. Yeah. Also, we have the tactile sensing capability. Still, we have a camera at the base, and we have a layer of elastomer covered on the sensor. And then we can sense the contact with these objects. So with the feedback, we can count these objects. So it's something like when you count your money. Yeah. So that's what we do in this work. So here we are not counting the money, but we are cutting the paper. Yeah. So we have done some ablation studies with the tactile feedback. If your task is counting like 10 pages, you can count 10 pages of paper accurately. But without tactile feedback, the droplet will fail. It can only count like 6 pages. So the previous ones are the hardware development in our lab. We have seen quite a few prototypes. We have seen the challenges embedded in data and the tactile data. So that's why we have developed a few works on how to transfer the data or generate data from one to another. And one recent work was the mode switchable vision-based tactile sensing. So the title is marker or markerless. So we can switch from a marker-based tactile image to markerless tactile image, and also vice versa. So on the left, as you can see, the input will be a marker-based tactile image. We have the markers. But in some cases, you may want to get the textures of the objects. For example, here, you want to see the texture of one object. You need to remove these markers from the tactile image. So here we propose this implanting method. So we first extract the mask of these markers, and then we remove these markers from the input image, and then we fill the removed areas with their neighboring pixels, yeah, with some generative models. And then we can merge all of these patches into a new tactile image without the markers. So that's the left flowchart for marker to markerless transition. Also for the other way around, we have the markerless tactile image. But if you apply such sensors for applications like grasping, the markers can give you some visualization results. It can help you to tell there's a slip, there's some relative movement between the grasper and the object. So that's why sometimes we may need these markers as well. Yeah. So here we use encoder-decoder framework. So we encode the features, the repetitions from the input markerless tactile image, and then we generate these movements of the markers in certain locations. That's how we can output the markers movements on the right. And here are some results. We have done some experiments for seeing objects and also for like unseen objects. So from the results, we can see we can generate these tactile images either with markers or without markers from the other domain. So this can help us to transit from one application to another. So with a certain sensor, so either with markers or without markers, it can be applied to different tasks. And also, this is from the other way around. We can generate these markers from the markerless tactile images. And here is a quick demo for this work. So this is the raw tactile value from this sensor. So we have a markerless sensor. And then we can generate these marker motions to the view so that we can know if there's a slip between the grasper and the objects. Okay. So that's what we have done for 2 different objects, and it can detect this slip in the tactile values. And that's one work. You have one sensor and then you can generate data of a different format, marker-based to markerless, and vice versa. Another recent work we have done for the hardware development is to use these generative models for the sensor. Yeah, so we have this new design. We have a multi-modality sensor. So it has a visual modality, and also it has the tactile modality. So here we have this tactile sensor with some pins. It's similar to the tactile sensor. So we have a few pins at the front. With that, we can have the proximity sensing. So using the visual modality, the camera inside can see through these pins and see the ambient world. Also, so that's the visual sensing. Yeah, so through these pins, it can see the objects that approach the sensor. On the other side, we have the tactile sensing mode. So by tracking the movement of these pins, so we can know the force involved in the interaction. So we have the normal force, and also we have the shear force. So that's for the force sensing. So in one sensor, we involve two modalities, visual modality and also the tactile modality. And here we have one architecture of our sensor. So we have this tape, so it's transparent, and also we have this marker, as you can see here. And we have a camera base, as we did for the other sensors. And here is a closer view of the sensor. So we have the skin, and we have the lights, similar to what we had before. And we have this indentation. When it indent the sensor, it can see the object shape, and also we can sense the force involved in the interaction. Okay? So that's the results we can get when we have the contact. We can see the letters from the object, and also we can track the force involved in the interaction. And with this hardware design, we have got some generative models. So we have one GAN. So for the left side, we can remove these markers. As in the hardware design, we involve both of these modalities. Okay? So in one line, if we want to have the visual features, we need to remove these markers from its camera view. Okay? So using this generative model, so we can train a model to remove these markers, and then we can get the visual features. On the other pipeline, so we have another generative model to remove the light. So as for the tactile sensing, we prefer to keep the movement of the markers, and then we minimize the impact of the ambient light on the sensor. So that's how we have this light removing network, and then we can keep the tactile features. When we have this perception, we can also fuse both visual features and tactile features to get a better perception. And here are some results for the marker removal and also for the light removal. So this is the first line are images for the original data, and then we can generate some image without these markers. You can see we can maintain these shapes without these markers. And at the bottom, so the inputs are the data we have from the sensor. And then we can remove this light, this embedded light, and then we can keep the movement of the markers. And here's a quick video to demonstrate this work. So this is an exploded view of the sensor itself. And then we have the camera view, the sensor structure. And then we have some tasks like creating identification. And here is for the pose regression task using different type of sensors. And also we have the force estimation. for these sensors. Okay, there's some quantitative results. Okay, so from the previous slide, so you can see we have got the hardware, and we have got some generative models to transfer the data from one type of data to another. So the next part of my talk will be the simulation. So one challenge in robotics is the data collected from the real world. It's the same for tactile sensing. For tactile sensing, we have a challenge in having these fragile elastomers. I believe you have experienced this in your lab as well. The elastomer is quite fragile. If you need a lot of data in your research, in training your robots, you have to damage a lot of elastomers. So one idea to mitigate this challenge is to use simulation. You can get a lot of data from simulation and train your robots in the simulation. And then you can transfer from simulation to the real world. So that's how we have the sim-to-real learning. Okay. So it's not only for the gel size sensor or GelTip sensor, it's for any type of tactile sensors. It's a common challenge for the tactile sensing. So we came up the very first simulation model for vision-based tactile sensors. So we have identified the most challenging part is to simulate the elastomer. That's the deformable one. That's nonlinear. It may vary from one sensor to another. Yeah. So how to solve it? So the answer in this work is to go around it. We didn't simulate the elastomer in the simulation. So instead, we get a depth sensor in the simulation. Yeah. So in the real life, we have an RGB camera to capture the deformation of the elastomer. But in the simulation, we get a depth sensor, and we remove the layer of elastomer. We don't have any elastomer here. And then we can get the profile of the object approaching this sensor. And then we get the depth map. With the depth map, we can render a tactile image in color with RGB lines, as we have seen in the real life. And in this process, we have a few steps. So first, we have the depth map, and then we can get some small sums, this contact map. As for the real life, this contact is a small sum. As you can imagine, for the contact, we have the Gaussian processing in the contact. Yeah. So that's why we apply Gaussian filtering to the obtained heat map. And then we have the normals for the contact area. And then we apply this illumination model to render this RGB tactile image. So that's the whole process for the simulation. And that's the very first work we have done for simulating vision-based tactile sensors. So on the left, we attach a gel size sensor to the end of a 3D printer. Okay? And then we apply this sensor against the 3D printed object. You can see here, this is the real tactile image we have collected from the gel size sensor. On the right, we create one tactile sensor in simulation, and then we get a simulated tactile image using the approach we have proposed. From this approach, we have got relatively good results. As you can see here, on the first line, we have the real samples from the gel size sensor. And this is the first tab. We just get the depth image, and then we render these RGB tactile images. And then we apply different Gaussians. As you can see here, we can have realistic contact areas around these contact areas. And across different objects, you can get realistic tactile images for the contacts. And also we can simulate different GelSat type of sensors. So like the original ones and also the GelSat 2017 ones with a different LED light setting. But for this work, we have seen some challenges, the real world challenge. So we can simulate the light settings and we can simulate the RGB tactile image, but we have found the real challenge lies in the imperfect real world. In the real world, for the 3D objects, 3D printed objects used in our work, we have seen these artifacts on the surface, like the lines caused by the 3D printing process. And we can't go around them as in simulation, you have a perfect surface. It's fully smooth. The very first approach we have got is to manually create some textures. We apply these manually created textures to the depth map, and then we can augment the data. And then we can see if we transfer such models from the simulation to the real world, the performance in object recognition tasks can be much improved. But that's manually created textures. And then following that work, we have created some generative models. So again, here we use a cyclogram. It's one type of the GANs, generative adversarial networks. So here we crop the contact areas from the depth map we have just seen in the previous work. And then we learn these textures from the real data. And then we apply such textures to the simulated tactile images. And then we can adapt it more similar to the real ones. And then with this adaptation, we can get more realistic data generated from these models compared to the simulation ones. Okay. And recently, we have extended this work using some more networks to simulate different elements of the tactile images. So we use MLP, a multi-layer perception mapping, to map these contact shapes directly to the tactile images. Also, we created some shadow functions to generate the shadows in the tactile images. In the previous works, we didn't consider these shadows, but they exist in the real world. So that's why we include these shadows in our new work. And also, we create some functions to simulate the distributions of the markers, and then we can simulate these marker movements directly. So these are some like pipelines for these three different elements. So with that, we can simulate very realistic tactile images in the simulation. As you can see here, with the shadow simulation, you can generate some shadows similar to the real ones, as you can see these edges. Yeah. And also with different contact depths, we can get a very realistic results for these contacts. And also we can get a simulation of these markers. We have created an object size with different shapes. So with different types of motion, like the shear force, the twist, so we can simulate these movements of these markers. Just to give you a quick view of the results. So here is here's an application of such models for packing hole tasks. So we train the model in the simulations with the method we just proposed. So we can simulate these marker movements, and then we can train this packing hole policy, and we can transfer such policies to the real world. So as you can see here, with the markers from the real tactile sensor, we can use these policies trained in simulation. So this can save our efforts in collecting data in the real world. So still you can see they can perform these packing hole tasks successfully in the real world with the policies trained in simulation. Okay, so in the previous sections, I have introduced how to generate data in the tactile sensing modality. Yeah. So for the last section, I will briefly introduce how to generate data from vision to tactile and tactile to another. And here we have collected one dataset. We call it VTAC dataset. So it's quite a long time ago, yeah, in 2018, but it has still been used by many of these recent works. So we used 100 pieces of fabrics, and we have two modalities. One is vision. We use a digital camera to take a picture of the fabric on top of the fabric. And then we use the GelFinger sensor to press these fabrics to collect videos of tactile videos of these fabrics. So in this case, we use the marker-based tactile images. And as you can see, we can see some common features in both vision and also the tactile data. So for example, these textures, these indentations for the fabric. So we have done one work on generating data from one modality to another. We call it touching to see and see to touch. So it's easy to understand. Yeah. So for one pipeline, we have tactile data, and then we use the generating model to embed all the tactile features in one these feature representations. And then using that feature representation, we can decode it into the visual outputs. On the right, as you can see, we have the visual image generated from the output. Similarly, if we have visual inputs, we have these textures, and we can encode these textures into another feature vector, and then we can decode this feature vector into tactile outputs. So this is the transition from one modality to another. And this is the networks we have used for these two pipelines. So essentially, they are the generative adversarial networks. So for the tactile to visual network, so we use the tactile image as the input. Also, we use this real visual image to get the adversarial learning. We take that as a ground truth, and by this adversarial learning between this generator and also the discriminator, we can generate more realistic visual images. So it's done similarly for visual to tactile network, and we can get more realistic tactile images as well. But it's not successful all the time. For many of the cases, you can get these tactile images or the visual images similar to the ground truth. However, there are some differences in these two modalities. So for vision, you have the color information, but you don't have color information in tactile sensing. So that's why if you have very diverse color information in vision data, so your generated tactile data may be very bad. So similarly, as when you do the transition from tactile to vision, if your desired output is very diverse color information, your result will be bad as well. Okay, yeah, I think I can conclude here. To wrap up, the goal of our research is to improve visual tactile perception through generative models, as we have seen in the talk. So we have done a few research strands. So the first one is the hardware. So we have developed different vision-based tactile sensors, including this mode switchable sensing. And we have developed different simulation models for the vision-based tactile sensing as well. And we have developed this data generation for visual tactile perception, from one modality to another. I also have some brief advertisements. One is one PhD studentship available in my lab. So this is in collaboration with Unilever. So the studentship funding comes from the PRC and also the Unilever. So it's on the development of tactile robots that can feel hair like a human. Yeah. So we have, as you can see in our in my talk, it's quite relevant to what researchers in Unilever do, as they have these products like shampoo, washing liquids as their products. So now they recruit people to assess these materials, but this can be costly and it can be of bears. Yeah. So that's why they have been working with us in developing these tactile sensors, assessing these materials. We have got 2 previous projects funded by Unilever, and we have developed some tactile sensor prototypes for Unilever product assessment. Here in this studentship project, we would like to invest in more how this behavior involved in the perception. Yeah, so it's an intervenient problem. And this is the industrial doctoral landscape award studentship. The stipend is higher than the normal ones. So even it's based in London at King's, you can get a good salary. Yeah. So if you know anyone who is looking for a PhD position, please share the words. And also we have this Accra VTech 2025 workshop. It has been a workshop series. It has taken place in the past years, and this is the 6th edition in this year. So we have got a long tradition of gathering people who are working on vision and tactile sensing as a community in this workshop. And this year in Accra 2025, we will have another VTech workshop, and we can discuss these topics related to vision and tactile sensing. Okay, thank you.
So, free to ask any questions you have.
Very interesting talk.
Okay.
I like the technical details about the sensors. I'm working on a research project where we want to ideally be able to measure small deformations and surfaces of structures and things, but we want to be able to do it in space under extremes of temperature and things. That made me wonder, for the gel site sensors and the systems you're using, is there a way that you can compensate for changes in temperature, maybe wear over time, if the gel becomes dimpled or deformed? Can you train the system to actually recognize that, compensate in the model for that kind of wear or environmental change?
Yeah, that's a very good question. Temperature compensation is a very good topic to investigate in this topic. So from what I have heard in the community, so researchers have reported if you use the gel site sensor for a long time, you may have the temperature problem, especially for the gel layer. Yeah, so this may impact the performance of the sensor in detecting the force. Yeah, but this from the inside of the sensor. What you just mentioned is more on the environment. Yeah. So I don't think there has been any research investigating that in the literature. One reason is that most of the research has been on grasping and manipulation with such sensors. But I think it will be a very good topic to investigate how the temperature will change the properties of the gel layer. Yeah. So we did consider this a few years ago when I was in Liverpool and I was involved in the RainHub, the robotics and AI for nuclear. So in that case, you have a similar problem. You may have the radiation, you have the high temperature, the property of the gel may get changed. Yeah, so I did some literature review and I think there was very little research on that. I believe it's more on like the chemical side, how you can investigate the properties of the gel will change across different temperature. And my assumption is that if you have a higher temperature at some points, it will get very rigid. Yeah, and it may not be able to detect the force.
Please. My question is, when you're going from markers, like markerless to markers,
Mhm.
is a you can have more than one solution, so you could have, and how do you choose which one it is, or it doesn't matter.
Mm,
So,
Mhm.
right,
Okay.
or is it that there's a unique solution?
So you mean which modes can I choose from? Yeah, marker on.
No, so
Oh.
if you're in the market, if you have no markers and you're going to markers,
Mhm.
how do you, can you have more than one solution for markers?
That's a good question. Yeah, so definitely you can have multiple solutions for the markers. You can have different patterns, like a circle or a ring. You can choose what you want. But usually for what we can see in grasping applications, usually we have a ring pattern. Then you can use this ring pattern to detect the slip and the force involved in the grasping. Yeah, but after all, we don't have a fixed solution for the markers. Yeah. So the only reason why you see this array type is the ground truth we have got in the transition is an array based. Yeah, but if you have a different type of markers, yeah, so you can generate different markers.
You don't have any additional question? I have some questions for you. So thanks very much, Sean, for the very nice talk. I can see that that your expertise is really complementary to what we have. One of the things I want to ask you, can you go back to page 10 of the presentation?
Yeah.
So
Yeah.
what I saw there is some black marker in the first page. Why is that necessary, or is just an incident? Because when you try to do it, it doesn't have anything for the later paper. But the first one you have a QR code
Yes.
in the first one.
Yeah.
Why? Why do you need that QR code?
So the main reason is that we don't want to rely on the vision to establish the first contact. We need to contact to
The QR
detect
code. Yeah.
to detect the edge, this corner of the page.
Okay.
Yeah. So that's why we call these QR codes
Yeah.
as the corner.
Okay.
Yeah.
Okay.
So when you establish the very first contact, you need to know where to before you get the contact. Yeah.
Put that in. Yeah. Okay. Great. Thanks very much. Then if you go to page 18, I'm sorry, I have lots of questions. I'm very interested in this.
Yeah.
So the question is, it seems to me that you have, correct me if I'm wrong, you have an image which contains both the image and the marker information, and you train two GANs to remove each one, and then you try to fuse them to have, because if you use the first one, it gets you only the visual features, and the second one, it gets you only the tactile features, so you can do analysis. So I'm just wondering, when I look at this, your image already contains two information. Is that possible that you can directly use that image to derive whatever it is? Because in the end, you still need to fuse them together.
Yeah.
So this diagram is somehow a bit confusing for me. Why don't you directly have one network which extracts whatever information that is from that image? Because it seems that it contains both.
Yeah, that's a very good question. Yeah. Actually, these two happen as different types. The first one happens when the object approaches the sensor.
Okay.
So that's why it's proximity sensing.
Oh yeah.
Yeah. So that's why you need to remove the markers to detect the object.
It's not the same image.
It's not the same image. It's not at the same time. Yeah. So as the bottom, so it's when the contact happens.
Okay.
Yeah. So that's why we want to remove the impact of the ambient light. Yeah.
Okay.
That's a very good question. We should improve this figure.
Yeah, I was just confusing. I think, okay, you have both, but why did you use one image? But I think it's my mistake, actually. And I think you at the last one of your research, you talk about you try to extract from vision to tactile, and you try to get from tactile to vision. It's also with your VTAC technology that you developed. So I think you also said the result is somehow this, but basically on your tactile data, based on tactile data, try to do this kind of transfer. See, you can see from one to each other. So from my understanding, if you prove this is extremely efficient, you can transfer from one to the other. That means one of the modalities is redundant. If you can really do that. So because you also said you cannot do it very well, I think in some cases, is it? Because if you just use vision image, because you try to get from your image, but or it is also like two different things when you try to one is proximity and the other is still touch.
Mhm.
Is it still two different things, or you are getting like
They are still two different
they're
things.
still two
They're
different? Okay.
still two different things. But in this specific work,
Yeah.
it was taken as a data mining problem.
Yeah,
Yeah,
so
it's a data problem.
Yeah.
We didn't apply it in a robotic context.
Okay.
Yeah, so that's why we're transferring data from vision modality to tactile,
Yeah.
and we check out the results
Yeah.
quantitatively. Yeah.
Okay.
But in a robotic setting, imagine that if you grasp one object on the table, so first you can have a glance of the object,
Yeah.
and you get the visual features,
Yeah.
and you can estimate what tactile feeling or tactile reading you can get when the contact happen.
Yeah.
So in that time, you have the thing to touch. You are imagining how the touch feels like.
Okay.
Yeah.
From the scene.
Yeah, from the thing. In that case, so this result, this conclusion still holds. If you have the vision, so you still have the noise. For example, the color. So with the color information embedded in vision, so it may not be very well in predicting tactile modality. Yeah.
Okay.
So, but I believe this will still be useful as you get your robot more prepared before the
touch.
contact. Yeah.
Okay, great. Thanks very much. My last question is that since that you are using the same the VTAC, if I'm not mistaken, you have vision before you touch, and then you have touch when you touch, right? So you have a bit of you can see that's what you can see the you have a proximity thing. But the thing is, I was wondering how far is the range of your proximity? So if you are really far away, can you still see, or no? So then what is that range?
So for the VTAC sensor, specifically, I believe the range is within a few centimeters. It won't be very far. Yeah.
Okay. So it sees probably the region where you send.
Yeah.
Okay. That's all for me. If you still have some questions. Yeah, please.
My question is about the simulation. So the only data from the simulator that you're using is the distance. So it's the visual. It's the visual that you're not using for physics. The simulator. It's just the geometry.
Yeah, that's true. Yeah. For this one, the raw data is the depth. So it means that's the geometry of the object. So we're not using the physics engine for the interaction between the object and the we're not as it can be very slow if you consider the elastomer deformation. Yeah. So that's why we go around it, and we only use the depth sensor to get the geometry of the object.
This would be used to could you feed it back into the contact solving physics engine and prove how realistic the physics engine is.
It can be done. Yeah, we have got some follow-up works. We simulated the deformation of the elastomer, and then still we have to render the tactile image, and then we can compare the simulated tactile images with the real ones. So that's what we have been doing. But I agree with you. Your viewpoint is more on if the physics work in this case. Yeah, yeah. So in that case, we have seen some works in this policy training. So in that case, there are different ways. So one way is to get very abstract repetitions in the simulation. For example, we use depth map, and we just disregard the RGB tactile image. So the aim is not to simulate realistic tactile image, but to turn the policy. to get that map and then we can follow it. It has been proven quite effective, as it's quite abstract, it's high level repetition. But if you involve this physics engine in this process, our experience is that it's not very effective, as the physics engine, they can't simulate the physical world well yet. And so that's why if you use a physics engine to do this, so the trend policy will have a very big gap with the real world. Yeah, to work on meditation. Ah, yeah, yeah. I can see how look at this question. Yeah, that's a very good one. Yeah, it's still an open question. So there are a few ongoing works in our lab. Yeah. Now I would like to hear your views on these works.
Well, I mean, there's kind of, there's very few contact models that use the physics engine that simulate this kind of thing. So it could actually be better for doing that kind of so we're close at the moment for rigid body contact anyway, it's like hydroelastic contact. I think this is like this is different for that.
Yes.
And maybe better for obtaining the data using this kind of sensor and using that data to simulate objects.
Yeah, that sounds interesting. Yeah.
Right, no further questions?
Yeah.
I'm very interested in the project of the hair detection
Mm.
With the sticker at that page.
Mhm.
And I have a question about that. Because when we trying to use the design to feel some very soft object, we will find if we touch it very soft, super soft, the visual tactile image is not that clear. So there will be little features for us to detect from these images. So when we feel when we make a very gentle touch on the hair, it may hurt if we drag it a little bit harder. So I think I'm very curious about how soft we use the gear to touch the hair, so we can get the features from the hair.
Yeah, that's a very good question. First of all, I forgot to mention, this picture was generated by ChatGPT. I originally included one notation here, but I changed my desktop to my laptop. That notation is not here, but this was generated by ChatGPT, not by me. So back to your question. So for the tactile robots, we have, as I mentioned, we have got two projects funded by Unilever. So we have done some experiments on how to address this issue. Yeah, so we did find the challenges in using such gel-based tactile sensors in detecting the contact with hair. So it's a multifaceted problem. Hardware, software, and also system. So we have made a few improvements in terms of hardware. So first of all, we got this mushroom head. So for the gel side, as you can see, it's a flat. So you have been using the flat surface gel size. If you use the gel size sensor to contact the hair, you can't get good readings, even if you apply a large force. Yeah. So that's why we have modified the shape of the elastomer to a mushroom shape. Yeah. So with a curved surface, you can get a better imprint when you apply the sensor against the hair. And also we have done different experiments with different coatings. So the coatings also matter. Yeah. So with the gel size coating, we can't get good readings. So that's why we have got different results, and we have found the transparent ones works better in our case. So we have a pending patent with Unilever for the hardware design. So back to your question on the fourth one, it's also related to how you apply the force. So that we found that there are different ways in assessing the hair. So at Unilever, they have got different ways to assess the hair, and they have got these FOTS plates, and that's a traditional measurement device in manufacturing industry. So it's a plate with some low cells underneath, and then the hair is placed on the FOTS plate, and then you can slide over the hair, and then you can record the recordings. So this FOTS measurement with the low cells. So as beginning, we had a very similar setting at the FOTS plate. We put the hair on a plate, and then we use the gel size sensor to slide over the hair. And then we found it's quite challenging to get good readings. We can see the fiber, but usually we can't get a very good FOTS readings out of that. So that's why we chose one end-to-end approach. We didn't predict the FOTS as the end. We just predict the ratings of the hair samples. So they have some comfort scores by consumers. So we just predict these scores out of the raw data. We didn't get the FOTS prediction. But this involves in the exome design. So in the future, we may investigate how the intermediate repetitions out of the network can give you better FOTS readings instead of just reading the raw data to get the FOTS.
Okay, I think it's time, and he'll be here for a while, so if there's still some questions, just go on Fanshan. I will just put him in one of the hot desks downstairs. So if you have any questions for him, but let's thanks for speaking.
Thank you. Thank you, Jim. Thank you all.
Okay.